Hi, welcome to the office hour of lecture 5, the inequality. So we are going to prove the homework, which happened to be harder than I expect. But maybe let's do it together. First of all, I'm going to show it in two ways that I taught in class. Right? And interestingly, you can also prove it in two other ways, which I will go over briefly at the end. Okay, so let's start from the two ways I told. We learned in class. For the first way, we have to use the two properties. And so first, if we know that the absolute value of some function is less than some value k, then it has to be between k and minus k. This is reflected by the distance. If the distance is more than it is bounded by this k. And the second one is if the distance, or if the absolute value is greater than k, then we have to separate inequalities. So we have, either this is greater than k, we can just remove it, or it is smaller than minus k. And so it has to be either too large or too small. Oh, and also let me note that this inequality, these compound inequalities, actually means that the function has to be greater than k, and we use the word and, the function also has to be less than k. And these are what we use to tackle this problem by going one step at a time. So first of all, we have two inequalities, which is kind of annoying, but we can deal with it one at a time. So in this example, if we think of this pink term as like k, just a little k, I just leave it as k, then that means we start from this inequality. We want to remove we start from this absolute value, and we want to remove the absolute value. It is in the first form, because it is less than some value. That means this gives us two inequalities. And those inequalities are, let me write it as k. So to mirror that, so we know that this function x plus 1 must be larger than k minus k, and this function also has to be less than k. It will be sandwiched between these two values. And now we can get plug in the value of k back. In this case, it is a function. Now we have two separate problems to work on. And now each problem only has one single absolute value left. Hopefully it should be easy to work with. Let's start from the left one. The left one has minus. Do we have minus here anywhere? No. So we must try to make it a plus. There are two ways you can multiply minus on both sides and flip the symbol. It's what I don't like. Let's do it this way instead. So you can add this term on both sides. And you get 1 here. This one cancel with the previous one. You get 0. And then you subtract this term on both sides. So you subtract both sides by x and 1. Minus x and minus 1. Now we have an inequality in the form of the greater sign, which is the second part here. Oh, and also that's also the second part where the absolute value is greater than another value. And so we can use this property or this theorem here to further break it down into smaller ones. Right? If you go here, we can just remove it, and that's one part. It can be, oh sorry, we need to remove it. So it's either very large or it's very small. So this value is very small, so it's smaller than this value, smaller than the negative of this value. And then just solve each of them, because now we entirely remove all the absolute values symbols. For instance, for the left part, you add x on both sides, you get 2x. You add 1 on both sides, you get 0. So you have x is greater than 0. And that's the first of the 4 we have to solve. And then what about this part? Oh, I think I miss another minus sign. So if you expand this term, you have minus times minus times minus. You get back to the plus side, so it's x plus 1. If you subtract x from both sides, you get minus 1 less than 1. And where is x? Now you ask. We are trying to find the value of x, but eventually we just remove them entirely. Maybe it's easier if you go back one step and look at this statement. And so we are trying to find a real number x such that x minus 1 is smaller than x plus 1. But this is always true. Therefore, any real number you choose, x plus 1 is smaller and x minus 1 is smaller and x plus 1 is larger. So this inequality always holds. That's why when you cancel, you get an inequality that is true. And this is always true. If it's always true, then that means that x can be anything. No matter which value of x you choose, this inequality or this inequality is true. Or in the set notation, you can have 0 to infinity. So that's the second part. And now remember that we have to combine them using the OR, because it's from this inequality, it's either the left or the right. And what are the value of x? So x has to be positive, greater than 0, or it can be anything. Okay, so it's positive or anything. That means x is anything. But for any value of x is always going to be satisfied by the second inequality. That means then the result is that for the left part, the solution is any real number. The whole set, it should be minus infinity. The whole real number set satisfy this inequality. If you want to do it systematically, so the left part is the set, and that's the solution. When you use the word OR, you take the union. And so you have this interval union this interval. But this it's just a small interval. The right hand side is already the whole interval. So when you take a union, you get the whole interval back. So what we got is, this is nothing. This doesn't tell us anything useful about what we want. And what we can is that the left hand side is always true. So we spend 5 minutes doing nothing. Okay, let's take a look at the right hand side, and hopefully it's gonna give us something interesting to work on. And so we already have it in the second form. So we can come here and write two similar inequalities. And so x minus 1 has to be very large, or x minus 1 has to be very small. Or. And similarly, let's solve the left one first. We have x plus 1 less than x minus 1. If you subtract x on both sides, you have x1 less than minus 1. What happens here again? What's going on here? X disappears again. But since this one is false, one is not less than minus 1. What this implies that no matter which value of x you choose, this statement is gonna be false. There is no x that satisfies this equation, or this inequality. which is actually clear if you go back one step. You want to find a value x that x plus 1 is smaller than x minus 1, or x plus 1 is on the left of x minus 1, which is impossible. So on the left hand side, there's no solution. So we can say there's no solution. Or as a set notation, we say that the set of solution is empty. There's nothing inside. Which is still okay because we have the word or. These two statements are connected with the word or, so you can still take a union and get something out of it. What about the right hand side? You do the math. You again distribute minus inside the parentheses. You get minus x minus 1. You add x to the left hand side. You get 2x minus 1 less than minus 1. You add 1 on both sides. You get 2x less than 0. Now you can divide 2 on both sides. You get that x is less than 0. That's the third solution. That's the fourth one. So now we get something meaningful here. We know that x has to be less than 0 half or. And so on this problem on the left hand side, what we have is we take the union. Right, so x is either in the first part, which is empty, there's no such x, or x is the right hand part. And we can conclude that x is this part. Says it's minus infinity to 0. So when you take the union, get this solution. And so that's the right hand side. And finally, we can combine these two. So remember that long time ago we have the and here. We say that it has to satisfy the left inequality and the right inequality. And we show both left and right separately. And finally, we have to take the and, which is the intersection. How do you intersect these two intervals? Or in other words, you have to find the value of x that x has to be x can be any real number, and x has to be less than 0. And so it's anything and less than 0. Which you can see this one is smaller. And so we only need this one to be satisfied. If you write in the set notation, like this, the left one, let's say it's the A, right? It's the whole line. That's the first solution. The second solution is only from 0 to infinity. Let's say that's B. Now we are looking for a number x that is on both sets and it's on both lines. And the numbers that are on both lines can be found exactly there. They must be on B. Because if it's to the right, then it's not on B. So we're looking for the numbers on B, or from minus infinity to 0. So this is the set of solution. This is the intersection of these two intervals. And therefore we have the final solution. This can be written as x less than 0. That's the first part. That's the first way of attempting this question, of this problem. You can use that's kind of long, but just as long as you follow step by step. And make sure you combine the solution using the correct notation, using or, and eventually you should derive the same conclusion here. So that's the first one, which took about 15 minutes each. Alright, let's take a look at the same problem and take a look at it in a different way. Remind that if we have an inequality of this term, we can interpret it geometrically. We can, if you think about them as numbers on the real line, and this implies that the distance, and this part means the distance between x and a. Right? If we say that it's less than k, and let's think about it. If we have the point A, let's say it's the number 3 or something, and we are claiming that the distance between a number x and this point A is less than k, that means we can go only to the right by the distance k, and to the left by distance k. We are looking for a number that the distance is not too high, is smaller than k, and that's exactly this interval, which you can see immediately that it is the interval from a minus k to a plus k. Or x is in the a minus k and a plus k. Is it actually the same as the definition where we say that x minus k is between k and minus k? And that agrees with our definition. But now we are going to look at them as points or as objects on the line. So let's see what is going on here. What we are claiming here is that the distance from x to 1 is greater than the distance from x2 plus to this point, which we have to rewrite as x minus 1. So now it becomes the distance between x and minus 1. Let's see which points satisfy those property. So we have these two special points, and we want the distance to this point. Let make it green. The distance from x to the point 1. We want that to be greater than the distance from x to minus 1. Which point should we pick on the line? Let's think about points. Let's say, for example, 2. You don't need to do the math to see that the distance from the pink to green is smaller than the distance from pink to blue. That's how the numbers work on the line. So here this green distance from 2 to 1 is smaller. It's much smaller than the distance from 2 to minus 1. Which means that this inequality is not satisfied. And you want this green distance to be higher than the blue distance. So that number 2 doesn't work. 2 is not a solution to this inequality. On the other hand, if you go to the other side, let's say if you take a look at minus 2, and now that the distance from 2 to minus 1 is only 1. They are close, but the distance from 2 to 1 is now 3. It's much bigger. And so that means this minus 2 is a solution. And the distance between minus 2 and 1 is greater than the distance between minus 2 and minus 1. Alright, based on these two observations, you can see, hopefully not immediately, that all the numbers to the right of 1 fails to satisfy this inequality. With the same argument, because the distance here is too small compared to the other distance. So all this thing doesn't satisfy that. And likewise, on the left hand side, all of this satisfy the inequality because the distance is much larger than the other distance. And so using the geometry of the real lines and the definition of the absolute value, we can see roughly which numbers are or not are these solutions. But then we have to we have to ask what happens in between. And the left and right part are obvious, but what about the number in between? And again, go back here and we want the distance to the green point to be larger. So if it's too large, if it's too close to green, then they don't satisfy the inequality. And let's say if we take this point, the distance to the green point, or x minus 1 here is 1, but the distance to the blue point is larger. That's on your eyes. And so this point doesn't work. It's too close to 1. And therefore we can kind of see that the solution must be this purple interval and extending from the left to some point. The question is to which point? It's a point that makes these two distances the same. That point happens to be 0. Because if x is 0, then the distance to the left and to the right are the same. And so it's only extend up to here. If it's to the right of 0, it's going to be closer to 1 than minus 1. And so it's up to here. And since we have a strict inequality, we don't have the equals here. So that means 0 doesn't count. Because if you plug in 0 back to the inequality, the distances are the same. But we want the distance to be larger. So we don't count 0. We make it a hollow dot. And thus, using this geometric argument, we can see that the set of solution is minus infinity to 0. Or to summarize it in a sentence, we say that the set of points that are closer to minus 1 than 1 is this set. The set of points that are closer to minus 1 than 1. The distance to minus 1 is smaller than the distance to 1 at these points. So this is the second way to solve this. And of course you are free to stop here, but in case you are curious how can we tackle this long inequalities, there are actually two more ways you can use. If we learn more about absolute values, then we can also use these two techniques. So one thing you can work with that is you can divide on both sides. And you let me say what? Why do we have to divide? Because at first we can divide because it is positive. And you don't have to worry about the negative value and flipping the sides. And you can safely dividing both sides by the absolute value of x minus 1. And this is what we have here. And whenever you divide, you have to make sure that you don't exclude it's not 0. You have to make sure it's not 0. And actually you have to first you might have to first say whether it is the one of the solution or not. If x plus 1 is 0, then we have x equals to minus 1. And if you plug x equals to minus 1 inside, it is actually the one of the solution. So we have to guess if x is minus 1, we have a solution. If x is not minus 1, then we can divide. And once we divide, this is where you have to know several properties. Like you can combine the absolute value side together. That's one giant symbol. Because again they are both positive anyway, so it doesn't. We can compute the ratio first and then take the absolute value to get the positive value out of it. And then you need to know how to deal with the fraction. You have to simplify this into smaller fractions. We replace x minus 1 by x plus 1 minus 2. And the reason we do this is because we want to get rid of x on top. And when there are more than one variable x, then it's maybe more difficult to deal with. So we want to get rid of it by splitting it into two terms. Yeah, that becomes 1. That becomes 2 over x plus 1. And here we have another inequality. This is easier to deal with because first we have only one absolute value. Second, we only have one single variable x. So let's do it. This is in the form of greater than, and the absolute value is greater than some number. So we know that it's either actually greater than that or this one is smaller than the negative part. And just solve it as usual. So we have this one greater than 0. So let's solve this left hand side first. And yeah, let's say we had the negative, so we move it to the right hand side instead. And yeah, this actually involves more absolute value properties. For instance, the thing is you cannot just multiply x plus 1 on both sides. Move the music stop. You cannot just multiply them on both sides, because if you do it, then this is what you have. And you have 0 less than 2, or 0 is greater than 2. It doesn't work here. The correct way to deal with this is you can multiply it by itself square on both sides. Because when you multiply it by a square, a square is never negative, so you don't need to worry about the sign flipping. So you can do it this way, and that becomes 0 less than what? This is square, this is just one term, so we have just x plus 1. And again, this is going too far from what we have learned and what we would need. But if you do it, eventually you get that x is less than minus 1. Right, we know that x is less than minus 1. Which doesn't look like what we had before, right? But let's take a look at this one. It's either less than minus 1 or this part. Right, so we add 1 on both sides to cancel this out. 1 plus 1 is 2. We add this term on both sides, so we get that. We can divide 2 on both sides. Get just that. And again, you have to be careful about multiplying x plus 1. The correct way, again, which is might be confusing if you have not seen this already, is that to multiply them by the square, preserve the sign and stuff. But then you're gonna be left with that. Notice that this becomes a square. This is one interesting part about this. We have only one x, but for some reason that turns into the square. So we actually need to know how to solve the square, solve the quadratic inequality. If you divide everything, you get that. So x times x plus 1 is less than 0. And we have two roots. We have minus 1 and we have 0. If the product is less than 0, it means it's negative. And there's only one way to get a negative number, which is in the small interval. If x is too large, they are both positive. If x is too small, they are both negative. But they have to be in between these two values. And thus the solution is that x is in 0 and -1 and 0. But if you combine these two solutions, you say that x is less than -1, or x is between 1 and 0. And this is the result if you divide them. It doesn't seem easier than what we have at first, but again, this is not what you are supposed to learn yet. And you can see that there's a hole. Something is missing from that equation. And indeed we do have the filler that to fill the hole. And we claim that everything here works if x is not -1. But we also say that if x is -1, everything still works. Right? So we still we also have to add the single value -1 from the case before we divide both sides. And finally, we get the whole interval from -infinity to 0. So that's the third way. And that avoids the issue of having 4 inequalities, but it does introduce some complexity of division instead. Okay, so let's take a look at the fourth one, and I keep the best for last. So we start from this inequality, and here you have to know another interesting property of the absolute value is that first you can square both sides. Usually you cannot square numbers on both sides because you have to worry about negative. You might have 2 greater than -3, but when you square them, they flip. Or sometimes you have 2 greater than -1, and you square them, they may not flip. So that's the issue of squaring things. If one happens to be positive and the other happens to be negative. But you can do it here because we are guaranteed that, because the absolute values, we are guaranteed that they are both positive. And if they are both positive, then you square it, then get shift in the same direction. So you can square them. Another property that we need to know before we can solve it is that we can remove, once you square them, you can remove the inequality sign. That becomes just a parenthesis. Why is it so? Because again, if you square a number, then it's positive anyway. So there's no need to put the inequality sign anymore. The inequality, the absolute value square is the same as the number itself square. No matter if it is positive or not. So that becomes this, and it is now a breeze to solve it. Because by the way we set up this question, everything cancel out, and so we get 0 minus 2x less than 2x. Oh, and be careful, you can divide by x. What you can do is we can slowly add x to both sides. So 0 is less than 4x. And now you can divide them by 4. And thus we get x less than 0. So that's the final answer, which doesn't involve any cases, any absolute value inequalities, because we get rid of them by the square. But that's another way to solve it. But let me note here that You cannot just always square. I said squaring things has a cost, but you can square if you are sure that they are both positive. If you know some properties about them. And yeah, that's a pretty long clip with 4 ways to solve the same inequalities. Right, thanks for coming to the office hour and see you next time.